Welcome to Risk Roundup. From photosynthesis to signal transduction, essentially all electronic processes in nature seems to occur in molecular form structures. Now, since the tools of molecular synthesis are advancing rapidly, the application of molecular building blocks for the fabrication of electronic components is gaining ground. Now, since molecular electronics use single molecules or nanoscale collection of single molecules as electronic components, great efforts are being made to duplicate the capabilities of silicon-based circuitry at the molecular level. As a result, there is a need to evaluate all available molecules that can be effectively used to develop molecular chips. And it seems that there is a great interest and potential in using DNA to generate molecular changes never imagined before. To discuss molecular chips further, I'm honored to welcome Paul Mola to this roundup. Paul is the founder and CEO of Roswell Biotechnologies and is developing a molecular electronics technology that will integrate single molecules as part of electronic circuits to deliver game-changing advantages to unlock precision medicine. And Paul is based in the United States. Welcome, Paul. We are so very honored to have you on this roundup.
Thank you, Jayashri. I really appreciate the opportunity and the platform to really present such a disruptive technology to the world.
Wonderful. No, it's my pleasure and honor here. So, Paul, before we discuss the molecular chips, let's talk broadly about the DNA economy and the emerging revolution. How close are we to the DNA economy from your assessment, from what you are seeing?
Well, I think our ability to read DNA and the genome of things in a very comprehensive and complete way is going to equip us with unparalleled knowledge just about how we function. Anything with a living, all living organisms have DNA. And so our ability now to leverage that information is going to impact us across various aspects of life. So I think of it more from, if you think about how we feed the world, how we cure the world, how we protect the world. These are all things that are going to be impacted greatly by this DNA economy. And I believe that in the next very near future, we'll start to see a lot of these come online and into the mainstream.
Yes, no, absolutely. I mean, if you look at synthetic biology or, this molecular electronics field, there are so many changes happening that focus only on DNA. And with the direct to consumer, DNA tools that are available, gene testing tools, that is also giving us a lot of advantage because we are collecting so much data. Now, it's if you look at the computer industry or the data industry, if we can say the digital data, there is a challenge that all these traditional hard drives or the digital format of data that is stored on the hard drives or on the physical drives that get corrupted or damaged in like 30-40 years. So there
Right.
is also a lot of focus on using DNA data storage. So once we start using DNA data storage, it's going to fundamentally change everything. And that will I was thinking when I read about your technology, that DNA reading technology, and I was thinking with the DNA data storage, if we are going to need DNA reading technologies, because you will need to read the data stored in so many different formats, in mobile and all different kinds of formats. So what you are developing is not just, I think, for precision medicine, it's going to be very, very useful for so many industries, for reading the DNA data that is stored, the DNA data storage, or even if we look at the bioterrorism that is happening currently, or it could be coming our way, if we have mobile DNA
Yeah.
readers,
Yeah.
then you can place that using the IoT sensor. You can place it at so many different locations, and you can get that intelligence in a timely manner. So we can quickly come up with that. Once we know what the sequences of the virus or pathogen coming our way, then we can quickly come up and find a solution, vaccine or some kind of treatment. So what you are developing is it has such a huge potential, Paul.
That's right. And one of the applications you mentioned, digital DNA data storage. If you think about it, nature has really optimized storage of information, and that is how information is passed from parents to sibling, and that has happened over many generations and millions of years. So nature has really optimized that, and we have an opportunity now to actually move from storing information, say, on a digital drive, or rather magnetic media. But now you use DNA to store that information, and if you think about, for example, the ability to have such high density storage mediums, that will transform the world, right? We all now are saving all our pictures and a lot of information. Each of us has a cloud drive of information. But what people don't understand, that we are actually getting to a point where the amount of information we generate, there's no storage actually to meet that demand. We are going to run out of storage, and so this is not a nice to have, but it is a reality that we need to transform our storage medium and have a new way to store information that can give us the density we require.
Yes.
What has also impacted the storage world is that we're in a place now where we are starting to I think we've all heard of machine learning and artificial intelligence, and how that whole world is transforming life and our lives today. It is relying on information, and you need big data sets, a lot of information. We are recording videos all the time now. Many cars have different sensors. You record temperature, video, etc. And so all this just upside of generating information must meet a technology that can store it appropriately and in an affordable way, so that we can actually then take advantage of these other opportunities, right? The one that is kind of interesting to me is when you think about, now we are talking about Mars and going to other planets. If you were to, and we all envision a world where we can go and colonize Mars, how will you actually take information to go 3D print a colony on Mars? You definitely do not want to be shipping hard drives, but you want a really dense medium like DNA. And just to give you an example, if you took all of the world's digital data today, generated since the world began to today, you can store all that in about something about the size of a sugar cube of
Yes.
sugar, right? So it's pretty dense. And so if you were to take that information, go colonize a planet, you really do not need a dense sort of a large number of hard drives.
Yes.
And so you're in a situation where you are actually now creating really different use cases, and providing us with an opportunity to actually use data in ways that we've never used before.
Yes, you are absolutely right. There's such a huge potential. The first point that you made about the storing of the data from one generation to another. If we are able to do it for several generations, we can study so much. Like we can,
Yes.
from the evolutionary perspective, this is huge, because that it will give us an ability to look at the DNA and the mutations that are happening, all the any changes happening at cellular level, DNA level. We will be able to study all that in the coming years, and that itself, it has such a huge potential. So when we look at all the potential of these, and it seems that you all at Roswell are converging. Not only just one advance, but advancements in nanotechnology, complementary metal oxide semiconductor technology, molecular biology, and material sciences, to realize this, potential of this technology, or the capability of reading DNA. So, what is the current state of the technology? Is it ready? Is it commercially available? How, and if it is, then how effectively can it read the DNA?
Well, it is quite a complex project, like you mentioned. We are converging the cutting edge of some of these advanced technologies, right? We are at the very bleeding edge of nanotechnology and the feature sizes we need to create. And the idea is that you need to create feature sizes that approach the size of a molecule. And so we're really pushing these technologies to the limit. And in some cases, we're a little bit ahead of the technology and waiting for the technology to catch up to us. So we have been successful in creating these molecular electronic sensors. These sensors are now being deployed on CMOS technology, and we have been working now to scale that to a point where we have enough pixels or enough density to actually read a full genome. A big part of the effort right now is optimizing the sequencing chemistry, and that is the chemistry that actually reads the DNA. It is essentially taking, in our case, the enzyme that has evolved in nature to make a copy of DNA. We take that enzyme and we actually tether it and integrate it into an electronic circuit. And then we are able then via that circuit to monitor what the polymerase is doing. And so if I were to give that polymerase a template, it's going to make a copy of that template, and I can actually observe that directly and electronically. And that's an important point because most of the technologies out there have relied on a chemistry that sort of translates what the polymerase is doing into a color change, and the color change is what you observe by taking a picture of it. It's very slow. The workflow is very difficult, but this is really observing that chemistry and converting the enzymatic activity into an electronic signature that we're able to read. So we're pretty happy with where we are and how the technology is evolving. We are stabilizing the sequencing chemistry, and we are looking forward in the next year or two to being in the market and giving at least the market an early flavor of this type of sequencing.
Good, good. So that's in very near future, 1 to 2 years. That's really good. So the one point that you made, the molecular sensors, are is that a potential of using those sensors on a level like IoTs? You know how IoT sensors are everywhere, being deployed. So would that be possible as a standalone sensor to be applied wherever we want to?
Yeah, absolutely. And so what we Roswell's competency is in integrating the molecules into circuits. So it is a platform technology that we can apply many different types of molecules depending on the use case. And even I envision a world where as CMOS technology sort of hits its plateau and scalability in terms of its shrinking capacity, I believe that there's a time and place where you can start to use molecules to even get more farther scaling of these technologies and getting greater densities and having then, in a couple of years, having a TV on the wall that actually runs on molecular electronics. So this is, you're right, the technology is a platform technology and with many applications possible. And we're just talking about for us, sequencing is the holy grail applications because of the implications on health and longevity, and so. But we are pursuing other applications as well that will enable us to. And one interesting one, for example, is you could have. The way at airports we have sniffing dogs and they smell out bombs and all that. That could be an electronic nose, right? So you could develop all sorts of applications that starts to pick and or integrate different sort of sensor enzymes and molecules that are found in nature, and using those then in the form of a circuit.
Oh my God. Is that real possibility? Molecular bombs, Paul?
Yep.
That's going to be pretty terrifying because, we will then need to come up with all kinds of technology to quickly scan the areas and to be able to find that. And right now also we are having challenges, to manage these kind of threats. So molecular bombs, that
But, yeah, and it's I look at it more from the aspect of sensing, right? And I think
yes.
you talked about, for example, when we talked about the technology being applied to feed the wild, heal the wild, and protect the wild. And the protect the wild comes from the perspective where you can actually deploy these sorts of sensors, right? You could have it sitting in the streets, or where you can actively monitor the environment and sniff the environment. And you could have it in the ocean on a drone going all over the place, and you could be sequencing in real time, you could be monitoring in real time. And because of the way the sensor is developed, it is literally very small. It doesn't take a lot of power. It's a very simple instrument, and because of this direct nature to sense.
No, I hear you. I think there is a real possibility that someone would develop molecular bombs, and we will need to be ahead, at least a step ahead to figure out how to stop those people. So that this is definitely a cause of great concern, and we will have to monitor this very, thoroughly. What developments are happening where the security risk could emerge. But coming back to the DNA reading technology. Do you think that this technology solution that you are developing, that it would be mobile someday and that it will be able to read DNA of any living being? I mean, not just to bring a sample in the lab and read the sample, but to have some kind of portable monitor, so we just go ahead and read wherever we want to read. Is there a potential of making it mobile?
There is a potential for especially making it mobile because of the miniaturization that is possible. You have a sensor, like I say, that is completely an integrated circuit and has very few moving parts. So you don't have your typical optical system with a camera that is very sensitive, and you cannot easily deploy that on a sort of a mobile sensor. But in this case, it is pretty much solid state and miniaturized. And because of also the simplicity of the workflow, it's very amenable to miniaturization and for mobile deployment, right? I see a world where the police cruiser will have its own little DNA sequencer. If they want to see if somebody is in the CODIS criminal database, they could easily just quickly, read that person's genome while he's still in the vehicle. Or you could have a situation where you're out in the field monitoring some really nasty infectious diseases for epidemiology or just for diagnostics. Or on the other case, if you're trying to monitor sort of for bioterrorism, right? You're out in the field, our soldiers are out in the field, they could have this in their backpacks and actively monitor the environment. So it's very, very amenable to that sort of miniaturization and deployment.
Yes, now that's a real possibility, like you say. I mean, these are early stages, so but there is a potential, and probably there is a need because we will need to develop a mobile solution. But now let's talk about the efforts where your focus is currently on precision medicine. So the current prevention and treatment of disease is not precisely tailored to each individual's unique capability or variability in genes or their internal environment or out external environment and lifestyle, because all those things are not possible to right now collectively evaluate. It's a complex process. So from your assessment, what is missing in the current approach other than the points that I just made, and what is your company's vision to transform, and how you are planning to transform this entire world of medicine from this new technology, molecular chips that you are developing or DNA reading technology, and uh, many other technological applications that you are developing?
Yeah, that's a question that's very near and dear to my heart, and that is one of the reasons that we started Roswell, is because of the impact for just improving our health and how we treat, how we diagnose people, and especially having the ability to tailor the medication and therapy to the person and not based on sort of a clinical trial that that has nothing to do with my genome, right? And so the problem with precision medicine today is that if you were to sequence your genome today, the utility of that information is not very much. And the problem is that we really don't know enough. So how do we get from this place of limited information to creating an encyclopedia where when I sequence you or I sequence myself, I go and look at my genome and compare it to the encyclopedia, and I look at a particular location and say, look, the encyclopedia tells me that if I have this gene, there's a potential that when I turn 30, I'm going to get cancer, for example, right? And so what to the bottleneck is the knowledge base. And to create the knowledge base requires that we sequence millions of people. And to sequence millions of people, you cannot do that when it costs $1,000 to sequence a million people. That's $1 billion to just create knowledge. It's very difficult to actually go to investors and try to raise money to create a knowledge base, because just the nature of it, and trying to put the return of your investment out in the future as a result. And so what Roswell's doing is we are attacking this problem by driving down the cost of sequencing, where you can actually decide today that I'm going to go get my genome sequenced, and that contributes to a database and a knowledge base. Or more importantly, we can enable projects like the Cancer Moonshot Project in the US, the Veteran Million Genome Project in the US, or the UK Genome Project, or the Saudi Arabia Genome Project. All these projects suddenly will be able to go and sequence their populations, and because these have to be national efforts, right? Because different populations have very unique genomes that are characteristic to that particular population, and so countries need to be especially then enabled to sequence their population, to catalog their population, and create knowledge bases that then are going to be more suitable for that population. By driving down the cost of sequencing, we will suddenly be able to do that. Our insurance company will say, well, if it's $100, if it's $10 for your genome, I'm just going to sequence you now. We'll keep that as part of your medical record. We'll learn from it, and as information becomes available, then you'll get a phone call and say, hey, this gene was discovered, you have it, and this is what it means for you. Or when you go to the doctor, you need a dose of aspirin, they're going to look at your sort of your pharmacogenomic, which is sort of your genome that controls how you metabolize drugs, and they're going to say, look, you need half a dose, you don't need, or you need twice the dose. Or by the way, if you take aspirin, it is going to be toxic to you, right? So these are this is what we'll be able to do with precision medicine, and we are at the forefront of enabling that by driving down the cost and also making the workflow very simple, such that you do not need to be a PhD to sequence a genome. You can have a lab tech or somebody with minimal skills actually be able to do that and have the data then analyzed.
No, that is certainly going to be disruptive, and it has a huge potential. So all these countries that you talked about, UK and Saudi Arabia, all those projects, are you all working together?
Yeah, these are projects that are happening globally, and I'm aware of some of the projects that I've been involved with, and I'm aware that there's quite a few projects that have samples ready to sequence, curated samples, but the cost barrier is too high, and so they're mostly waiting for the cost to drop. And so this is important, because once getting and biobanked and ready to go is the bigger problem, and then now having a sequencer that can just go and apply to the samples, then that's going to be the next step.
Yes, very true, very true. No, that there is a huge potential, and coming down, of course, I mean, $100 for analysis, that is going to be pretty transformative. And I think you're also focusing on reducing the speed, right? I mean, you talked about that it would be very simple, that anybody with, basic skills can, learn to, do the sequencing. You don't need a PhD for that. So that itself is a big transformation. And on top of it, if it takes just a very little time to do the test, then it's pretty useful, for all those tests that needs to be done all across nations. And we need a proper data accumulation, data analysis. So that is going to be very transformative, Paul. And congratulations on working on this and coming up with a sensible solution. Now, we talked about using the DNA as a molecule for these molecular chips, but I was reading that there is also a lot of efforts going on to using protein as biochips, and there are also a lot of hydrocarbons that are being used, and there are also several other things that are being tested. So when we talk about protein biochips in comparison to DNA biochips, especially for personalized medicine, is your focus strictly on DNA biochips, or you're also focusing on protein biochips?
No, we essentially have four of the above, and the way we would like to think about Roswell is like I said, have competency in integrating all sorts of molecules into circuits, including peptides or proteins for that matter, and DNA and other molecules. And so it really is a question of what is the application, because for some applications, DNA is sufficient. For others, you need a peptide. For others, you need a other material. And it's all about signal to noise and being able to sense above the noise. And so these are it's mostly dependent on the application you're developing, what exactly is the sensor, and then you have a choice of sort of pieces to put together and assemble the sensor.
Yes, yes, no, very true. Now, I mean, when we look at biochips, molecular biochips, and if you look at the molecular synthesis, the tools of doing this molecular synthesis, it looks like, they are quite advanced now. And but there is still, certain, drawbacks that, in there, some of them are still unstable at high temperatures. So the setup that you have for, DNA technology that you're developing, DNA reading, and all that, are they stable at high temperatures, or you need, into some specific, temperature range?
No, these are since they are biomolecules, you tend to operate within a given temperature regime, and this is pretty much ambient temperatures are sufficient, and that's where we operate. So we really don't have a problem with excessive temperatures in our on our system.
That's really good. So when we talk about the circuit, if you are developing a biochip, DNA biochip, you also need to develop the circuit. So has that been already tried to develop the circuit for the DNA chip?
Oh yeah, we definitely have advanced programs that the sensor itself is a discrete sensor, but then you deploy that on a circuit, and the appropriate amplifier boards and voltmeters that you create and build them as part of your integrated chip, and then you deploy that on CMOS and scale it. So this is all as we started. We said it's multiple sort of competences and bringing together then the CMOS, the electronics, the nano sort of fabrication, and all the software that all ties all that together. So those are all part and parcel of the development we're doing at Roswell.
Good, good, good. So now, when we talk about the molecular charge transport for the when we develop the DNA chips, what is the mechanism behind it?
Well, this is you ask a good question, right? This is something that is going to need to be studied to fully understand the mechanisms. We are still really just starting to understand. Is it electron hopping? Is it tunneling? This is what we're trying to fully comprehend, and we will be publishing on this in the next couple months. So stand by for an update once we're done with those experiments, and hopefully we'll be able to shed some more light on that.
Good, good. I look forward to reading that. So now, when we talk about where you are in the technology development and all these different projects that are going on at Roswell, what are the key challenges you are facing to reach the vision that you have as a company?
Well, I think the key challenges are recruiting. We're in a very competitive market. We have Qualcomm, Apple's opening shop here. We have so it is difficult to recruit and retain talent, and so we're very fortunate that most of the team who's come and been part and parcel of Roswell are people who really believe in the mission and the vision, and so creating a culture that is empowering, that is supportive, that allows us to take risks and fail fast and learn fast is very important. On the That's on the people side. I think on the technology side, definitely the nanofabrication was a big challenge for us. And like I said, we're a little bit ahead of where the technology is in terms of nanofabrication. which means we need to play quite a few tricks to nanofabricate at the feature size we need to work at. And so that's been one, and the other one is really in the material sciences space, right? So you're trying to take a biological molecule and then make it part of a circuit, and that's not a trivial problem to have. You can imagine if you took yourself and you plugged yourself into an electrical circuit. There's a lot of things you have to worry about, and so we are unfortunately at the we're pioneers in this area. So there's a lot of learning to do, and no one's really operated at this regime, and so we just have to be patient and innovate and fail fast and learn. But it's all about a lot of these advanced concepts.
Absolutely, absolutely. There is a lot of patience required. You are right there. So what would you like to tell our global viewers and listeners, especially about what they should be expecting? Like, you said in a couple of years you should be able to publish, a lot of. I don't think you said couple of years in near future to publish some of your results, and then you should be ready for the technology,
Mhm.
the DNA reading technology in probably a couple of years. So. In addition to that, what would you like to tell our global viewers and listeners about Roswell Technologies, or where they can, go to get more information, or if they want to get involved in your research or to collaborate, where they should reach out?
Well, the website, roswellbiotech.com, and that's ROSWELL biotech.com. We have information on the website, as well as an ability to contact us right from the website. And like I said, I think it's great to be part of a brand new sensor technology. And I believe that in the next couple of years, that when you go to college, there'll actually be a subject, molecular electronics, and training people that have the ability to then actually create even more technologies using and leverage types of sensors, or even just the technology itself, one day being in just sort of our normal electronics, like on your phone or on your computer or your TV at home. And that's where I think it starts to get into the mainstream. So mostly we just the interest, and we look forward to getting this technology out in the market, and where people's lives are going to be impacted, and that's what makes us do this and every morning.
Yes, very true. People's lives are going to be impacted, and this is disruptive. It has a revolutionary potential, no doubt about it. It will disrupt many industries, not just precision medicine, but many industries, and also would create bigger complex challenges for security professionals like me. Because this is going to create a security nightmare. It will be very difficult to monitor or keep track of all these molecular size bombs and sensors and breaches that would happen. So hopefully that we are able to come up with effective solutions by the time you all are ready, innovators like you are ready, so that we can have a parallel balanced growth, and we can manage the risk coming our way. So thank you so much, Paul, for participating in Risk Roundup today. We
It's been a
appreciate
pleasure.
we appreciate your thoughtful insight on molecular chips and helping us raise awareness of this critical topic. We thank you for that.
You're most welcome. Thank you.
Also, Risk Roundup, a global initiative launched by Risk Group, is a security risk reporting for risk emerging from existing and emerging technologies, technology convergence and transformation happening across cyberspace, acquired geospace, and space. We at Risk Group believe that risk management, security, and peace, they walk together hand in hand. Though security is related to the management of threats and peace to the management of conflict, risk management is related to management of security vulnerabilities as well as management of conflict. And it is not possible to conceive any one of the three without the existence of the other two. All three concepts fit into each other. We believe that the security we build for ourselves is precarious and uncertain until it is secure for everyone across nations. Tradition becomes our security. So, if we build a culture of managing risk effectively, it will lead us to security, and security will lead us to peace. Let's manage the existing and emerging risks together. For more information on the risk roundups, to watch the risk roundup videos, or hear the risk roundup podcast, please go to riskgroupllc.com and do not forget to subscribe and share. Until next time, I'm Jayshree, host of Risk Roundup, signing off. See you next time. Thank you.